Most of the time, the surface of our world gives no hint of what lies below. But there are a few places on Earth where we can get a glimpse of what's happening inside the planet.
That is just one fantastic sight. You can really see how much of this cone has fallen in. These talus slopes are all very recent. Like all the loose boulders we see down here have fallen off the crater walls since March.
This is Mount Kilauea on the island of Hawaii. Scientists from the US Geological Survey regularly fly up here to keep an eye on the lava pond. But to get that key, scientists would have to perform an ingenious series of experiments which would take them deep into the planet's interior. The first step was to get hold of some rock from the mantle. It's rare stuff, but just occasionally volcanic eruptions bring to the surface small unmelted fragments of the mantle.
Do you often find such objects?
Well, I mean, while you walk around
Eckhard Sallier spends his time studying them.
places, you will. In any sort of volcanic event, you have a certain chance to have some basalt coming up. And sometimes, when you're very lucky, you find these green patches on here. And this green material is actually olivine.
So this is the lava material, and that's really a piece of the Earth's mantle,
Which was stuck into it and transported with it up to the surface.
And what is olivine?
Well, olivine is a silicate, has magnesium ion and so forth in there. Normally it's very fine-grained, as you can see there, but if you're really lucky, you can find crystals of that. Yes, they're rather big and nice. Again, this typical greenish color.
Yes. That's pure olivine.
That's pure olivine, yes.
Yeah.
Now, they are nice, but of course they don't tell us very much as they are about the conditions as they are down in the Earth.
Because normally this stuff is existing at very high temperatures and pressures.
That's right. And what we want to do is to simulate the same conditions, but in the lab.
So a tiny sample of olivine is squeezed between the jaws of a specialized vise called a diamond anvil. To understand how pressure affects the sample, Eckhard uses X-rays to look deep into the structure of the crystal. As scientists employ these techniques to descend ever deeper into the Earth, they're revealing how the behavior of our planet is governed by what happens at the atomic level inside the mantle. Although the sample always remains solid, the intense pressures can disrupt the structure of the crystals. And that means the solid material can slowly flow.
Suppose this is a piece of the Earth's mantle. Seismologists tell us, based on earthquake observations, that this material is solid. It's elastic. It's resilient. What could be more elastic or more resilient? However, on a longer time scale, its behavior is completely different. So the mantle of the Earth is both a solid and a fluid. It's all a question of time scale.
So over long periods of time, the solid mantle is flowing. But what does this flow have to do with the motion of the plates? Scientists would find the answer to that when they voyaged even deeper, down to the iron core.
We have here a piece of iron in which we're going to recreate the conditions at the center of the Earth. And we have to do that by generating very high pressures, and we have to melt it under those very high pressures. And we're going to stick it in this, the hydrogen gas gun. Now Keith is loading the gun now with about 7 pounds of gunpowder. When the gun is fired, it pushes this heavy piston down this hydrogen-filled tube, which starts out at 10 times atmospheric pressure, but the time we arrive here, it's about 2,000 times atmospheric pressure. Takes this disc, bursts it, the hydrogen comes out of here and pushes on this projectile, accelerating it down this tube, up at about 10,000 Gs, up to a velocity of about 8 kilometers a second, which is why we call it the fastest gun in the West. Once it gets here, it impacts on the target, generating very high pressures, melting the iron target, and Chungshik U has about 50 billionths of a second. Measure that temperature. I'll zero the counters.
Neil Holmes is going to all this trouble because he wants to answer a very basic question about the Earth's core.
These set.
How hot is it?
Okay, everything looks good over here.
Since scientists are pretty sure that the core contains molten iron, the thinking is that its temperature must be close to the melting point of iron.
Okay. Calibrating target chamber.
But not the melting point at the surface.
Bringing up X-rays.
The melting point under the stupendous pressures at the center of the planet.
Okay, whenever you're ready, Keith.
Ready to fire.
Yes, go ahead. Yeah. Well, there's not much left in here. That used to be a part of some of it. I don't know what. So the whole target, everything we started with, is destroyed. But when the projectile hit the iron made a brief flash of light. The color of that light tells us what the temperature was. What it tells us is that melting temperature is 6,200 centigrade. This is over 1,000 degrees hotter than the surface of the sun. What this means is the core of the Earth is a glowing ball of hot iron, 3,000 miles in diameter. And slowly over the eons, that heat is gradually moving out toward the surface of the Earth.
So at the Earth's center, beneath the mantle, there's a heat source hotter than the surface of the sun. Anybody who's ever put a pan of water on a stove knows that when you heat a fluid from below, it starts moving. A little bit of dye shows what happens. Hot material comes up from the bottom, rises to the surface where it cools and sinks back again. This is the process known as convection. To geologists, the obvious question was, is this what's happening inside the Earth? Now, it was Lord Rayleigh in the 19th century who discovered that convection depends on several factors. One, the thermal properties of the fluid. Secondly, the viscosity of the fluid. And thirdly, how deep the layer is. Now, thinking about the mantle, we know how deep the mantle is from the earthquake evidence. We know about the thermal properties from the work that's been done with diamond anvils, and you can get a good estimate of the viscosity from the speed with which Scandinavia is rebounding after the pressure of the ice has been removed. When geophysicists plugged these values into Rayleigh's formula, they discovered that not only can the Earth's mantle convect, it must convect, and must be convecting very vigorously.
So the situation now is really very much more interesting because we have this mobile Earth, which is mobile because it's transporting heat from the interior towards the surface, both upwards by hot material rising and downwards by cold material sinking. And the thing acts really just like an engine, right? It's converting heat, right, the heat which it's transporting, into some sort of work. And it's this work which is driving the plates around on the surface.
It's not difficult to see how the motion of the plates relates to convection in the mantle. At the mid-ocean ridges, hot mantle is flowing up, and as it cools, it forms new plate which moves away from the ridge. Eventually, it's cold and dense enough to sink back down again into the planet's interior. So the complex motion of the plates is actually part of a simple process by which the Earth is slowly losing its massive store of heat. But what about the volcanism in places like Hawaii? How did that fit into mantle convection? When Dan Mackenzie started experimenting with convection, he made a totally unexpected discovery.
What we wanted to do was actually see what the general sort of things that fluids like the Earth's mantle could do. So what we wanted was a fluid, right, which had properties which were like those of the mantle. And the one we chose was Lyell's golden syrup. The arrangement is that you have hot water underneath, right, here, which actually causes this layer of syrup to convect, because it's heated from the bottom by the water and cooled from the top, right, by the atmosphere. And we can see what's going on by shining light through this layer onto the mirror at the bottom, and then makes an image on the screen. And you can see the dark parts on the screen are where hot fluid is rising, and the bright ones are where cold fluid is sinking. So it comes up in a plume in the middle and then goes down around the outside. And you can see that the whole of this screen is covered with all these little cells. We could heat it in different ways, right? We could do all kinds of different things. We could alter the top temperature and alter the viscosity contrast. Really doesn't make much difference, right? You always get this pattern. Lots of little cells. Not really at all like what we wanted for plates.
That's a bit perplexing at first sight.
Yes, yes, absolutely. Well, it was also rather a disappointment, right? Because what we really wanted to understand was how we could drive the plates. But this then gave us the idea that maybe on Earth the same thing was going on, and that underneath these big plates there were perhaps lots of little cells like this which were convecting.
Could one of Dan Mackenzie's convecting cells lie beneath Hawaii? If so, then all this lava is coming from a plume of mantle rock that has risen from deep within the planet.